A solution is any homogeneous mixture of two substances. So recall from chapter 1 that a homogeneous mixture is one that has uniform and unchanging composition. Every sample will be the same. You usually cannot see the individual parts of the mixture. So those are all hallmarks of a homogeneous mixture. A solution is made of a solute, which is what gets dissolved, and the solvent, which does the dissolving. Solute and solvent both can be any state of matter. We tend to think of it as a solid dissolved in a liquid only, but it can be any state of matter. It can be a gas dissolved in a gas. It can be a gas dissolved in a liquid, liquid dissolved in a liquid, any state of matter. Air is a homogeneous mixture, and so it's hard to tell what the solute and the solvent is with air. But another way to distinguish between solute and solvent is that solute is what there's always less of in the mixture, and the solvent is always what there is more of in the mixture. So air is mostly nitrogen, so nitrogen is the solvent, and oxygen, carbon dioxide, water vapor, other trace amounts of other gases are all the solutes. Aqueous solutions is mostly what we're going to be dealing with in this chapter, and an aqueous solution is one in which water is the solvent. Qualitatively, solutions can be concentrated or dilute. A concentrated solution has a relatively large amount of solute, and a dilute solution has a relatively small amount of solute. But it's relative, and it doesn't really tell us anything about how much of the solute there is. And in chemistry, we most of the time need a more quantitative way to describe solutions, and so we use molarity. The formula for molarity is the amount of solute in moles over the volume of the total solution in liters. So a simpler way to write that, molarity is moles over liters. So when you are preparing a 1 molar solution, you weigh out 1 mole of the solute. So in this case, I weigh out 1 mole of sodium chloride. I add it to this thing that's called a volumetric flask. I add some water to dissolve the solute, and then I fill the flask to the 1 liter mark so that I have 1 liter of solution, not 1 liter of solvent. So molarity again is moles of solute over liters of solution. So when we are solving these problems, we're going to employ the guess method, guess standing for given. So I'm underlining my given. Unknown, circle my unknown. Equation, what equation am I going to use to solve this problem? So I'm using my molarity formula. Set up, go ahead and write out what all of your variables are. So I have a 2 molar solution. I don't know how many moles, and I have 3 liters of it. Solve, you would just go ahead and plug into that equation. So 2 equals x over 3. Multiply both sides by 3. And so x equals 6.0. And the unit on that is just a capital M, which you read as molar. So we'd say this is 6.0 molar. I'm using 2 significant figures because both of my given numbers were 2 significant figures. If they're different numbers of significant figures, remember you always go with the fewest. If algebra solving is not your strong suit, it might be easier if you plug these numbers in, put that over 1, and then cross multiply, and that would work regardless of what variable you were solving for. So you could just always solve them that way. So again, I'm given 25.5 grams of potassium bromide, 1.75 liters of solution. My unknown is the molarity. Equation, molarity is moles over liters. Setup, I don't know my molarity. And I'm not given moles, I'm given grams. But I know how to convert from moles to grams, right? So I get the molar mass off the periodic table. And I get 0.214 moles. And then my liters is 1.75. So then I go to plug it into my molarity formula. Molarity is 0.214 over 1.75. So that is going to give me a 0.122 molar solution. Again, 3 sig figs because both of my given numbers had 3 sig figs. In this one, I'm given the volume and I'm given the concentration. And I want to know how much potassium bromide do I need to weigh out. So weigh out meaning, of course, that I'm solving for the mass. Equation is still molarity is moles over liters. Setup, my molarity is 1.50. My moles is unknown. And my liters is 250 milliliters, which you would then have to convert to liters. So when you're plugging into the molarity formula, you have to have the units of moles and you have to have the unit of liters. So I'll go ahead and plug in 1.50 equals X over 0.2500. Put that over 1, cross multiply, and I get 0.375. And the unit of that, the unit of X, was moles. This is asking me for the mass. So I have to go one more step and convert to grams. And so I will get 44.6 grams. 3 sig figs because 1.50 was 3, 250.0 was 4, but you always go with your fewest. And then lastly, we're going to solve for liters here. So I'm given moles, given concentration, solving for liters. Molarity is moles over liters. My molarity is 0.125. My moles is 0.255. My liters is my unknown. So 0.125 equals 0.255 over X. Put that over 1. Cross multiply, you get 0.125x equals 0.255. So X is 2.04 liters. To save space in the chemical storage room, we store stock solutions, which are highly concentrated solutions that then we dilute to whatever concentration we need for a particular lab. So when a solution is diluted, when I'm just adding water to a solution, the moles of solute does not change. So the moles of solute at the beginning, before I dilute it, we'll call that mole 1, is equal to the moles of solute after I dilute it. We'll call that mole 2. If I rearrange the molarity formula, I can see that moles is going to be molarity times liters. And so just doing substitution there, substituting that into mole 1 equals mole 2, I get the formula for dilutions, which is molarity of the solution before the dilution times the volume of the solution before the dilution equals the molarity of the solution after the dilution times the volume of the solution after the dilution. So M1V1 equals M2V2. Just like before, this is always talking about volume of the total solution. So if I'm diluting, I will put the amount of stock solution that I need into my volumetric flask, and then I will fill that volumetric flask to the correct mark with water. I do not add like 1 liter of water. I want 1 liter of total solution, or in this case, 3 liters of total solution. So using that formula, I'm given a liters, a molarity, and another molarity. And it's asking for how much, aka what volume. So based on what I'm given, based on the fact that I'm given a volume, molarity and another molarity, I know that my formula is M1V1 equals M2V2 because that's the only formula I have that has 2 molarities in it. So writing out what everything is, M1 is 0.5, V1 is 3, M2 is 10, and V2 is my unknown. And then just go ahead and plug that into the equation. So 5.5 times 3 equals 10 times x. So we get 1.5 here equals 10x. Divide both sides by 10. X is 0.150 for sig figs, 0.150 liters. We know that the unit of the volume is liters because my other volume was liters.